The next generation of global power isn't being sketched out by human scientists at a drafting table. It is being hallucinated by code. For decades, solar energy research was defined by grueling physical labor. A researcher would hypothesize a new material, synthesize it, bake it onto a substrate, and haul it onto a roof to see if it captured sunlight. Testing a single variation of a solar cell required building it from scratch. Every new idea meant months of delays, constrained by the speed of human hands and chemical reactions. Machine learning completely bypasses the physical lab. Instead of mixing actual chemicals, algorithms screen millions of digitized material combinations inside virtual environments. Physical research reached its absolute speed limit. Scientists now move the discovery process into virtual spaces, where algorithms can iterate through designs in milliseconds. This graphic illustrates Scale 1, the atom. To find the perfect molecule, researchers use high-throughput screening. As highlighted here, an algorithm can analyze 432 million donor and acceptor pairs instantly, discovering a new perovskite structure that boosted light absorption in under a week. This diagram shows the ensemble of machine learning models driving this speed. The random forests model predicts energy conversion efficiency purely from data, bypassing the computationally heavy equations physicists used to rely on. Material discovery has become a high-speed data operation. Timelines have collapsed from years to days. Even with high-performing raw materials, standard silicon solar cells hit a physical barrier, called the Shockley-Queisser limit. This caps theoretical efficiency at roughly 27%, with extra solar energy lost as heat. This diagram shows how AI engineers around that barrier using tandem cells. Notice the tandem light net. The AI perfectly matches the band gap of each layer, so different layers capture different wavelengths. These optimized designs reach conversion efficiencies of 32.5%. The algorithms take raw molecules and engineer multi-layered architectures that surpass the established boundaries of traditional solar technology. A high-efficiency design is only useful if it can survive the assembly line. The transition to mass manufacturing often introduces microscopic defects that ruin a cell's performance. This schematic illustrates the solution. Convolutional neural networks act as an AI eye, visually scanning continuous sheets of solar film in real time. As the readout details, they detect microfractures and contaminants with 98.5% accuracy, beating human inspectors. This flowchart maps out what happens next. The machine learning model actively feeds visual data back into the system, continuously modifying production settings on the fly. By adjusting settings based on real-time data, this closed-loop process cuts material waste by 20% and lowers overall production costs by 8%. We have automated the invention of the solar cell, its mass replication, and its optimization on the factory floor. We have record efficiencies and optimized factories. But this rapid pace comes with a heavy intellectual cost. Deep neural networks can output perfect solar cell blueprints, but they cannot explain the underlying physics or chemistry of how they arrived at that answer. It is a true black box. This creates a crisis of interpretability. Scientists are now synthesizing and deploying complex chemical combinations without actually comprehending why they function. If an algorithm discovers a revolutionary new transparent conductive oxide, the patent system fractures. We no longer know who actually owns the discovery or how to verify its long-term stability. Humanity is shifting from being the primary architects of energy technology to the operators of systems whose internal logic remains obscured. We must now consider the implications of handing the future of the global power grid over to an intelligence that humans can no longer fully interpret.